introduce us to photonics. Thank you, Mark.
Thank you very much. You're absolutely right. I do have an undergraduate degree from mechanical engineering, and I still remember the boiler tables that we had in those days. At any rate, it's a pleasure to be here, and I want to thank the organizers of the program in complex analysis for inviting me and to give this lecture. It's really an honor. So, today's lecture, Extraordinary Waves, Math, from Beaches to Photonics. Well, I'm going to talk about a certain class of waves, because you can't talk about all waves. I mean, it'd be impossible. But here are some of my thoughts. First, of course, waves have always held people's fascination. And just as an example of this, these two prints by a Japanese artist, Hokusai, the fast cargo boat, which is earlier in his career, and the great wave off of Kanagawa. The latter is one of the most famous of all Japanese prints. And here's the first one, big wave. I don't know how fast that cargo boat is, but it's an awesome wave. And today we might call it a rogue wave. I'll talk about those later. And there's this great wave off of Kanagawa, and most of you have seen that. And you can buy T-shirts, you can buy pants, you can buy coffee cups, all with the great wave on it. What's this lecture going to be about? Well, I'm going to introduce the subject, some background, history, and waves that are nonlinear, and I'll talk about what I mean by that, especially those called solitons, because I have to limit to some degree what I'm going to talk about. And math underlies these studies. And though I proudly have a degree in mechanical engineering, my thought process is always mathematical. And summary. So, linear waves, well, they're small amplitude. Nonlinear waves, the amplitude is not small, significant. We're going to talk about either solitary waves or solitons. Now, I'm going to make a difference between a solitary wave and a soliton. Historically, we know there's a big difference, and this is really a development of mathematics, what happened with solitons. But solitary waves is how things started, and for many years that's all people used in terms of the nomenclature. But after solitons got developed, understood, I would say workers in more applied areas took the word to mean anything that is a localized wave. So a localized stable wave, not a wiggly wave. You go to the ocean, you see wiggly waves most of the time. We're talking about localized waves. And they are solitary waves or solitons. I'll make a distinction most of the time. Math-wise, solitons satisfy nonlinear equations. And in the mathematical context, they are very special. They're integrable. They can means we can get solutions. We can linearize certain initial value problems. Some fields where they arise, water waves, optics, probably the two most popular these days, plasma physics, Bose-Einstein condensation, and problems in pure and applied math that grows very deep. Now, the concept of solitons, for some strange reason, become very popular. If you go to Google, 2 million results. Google Scholar, 400,000 results. That's a lot of numbers. We're not talking about all 2 million results in dealing with mathematics. No, it's not the case. There's soliton. There's companies called Soliton Technologies. This is a machine vision company. There's a lab art gallery. And you have this Star Trek Season 5, Episode 10, where they participate in a new propulsion method called the soliton wave. And I have this guy here for you. I apologize that the voice isn't so good. When we got it, my student got it a while ago. He was a...
We're approaching the planet Thalama 3, where a new method of propulsion known as the soliton wave is being developed. The Enterprise has been asked to participate in one of the first tests of this new technology.
Data, isn't this exciting? We are going to witness a moment in history.
Every nanosecond in this continuum is a moment in history once it has elapsed.
No. I mean, we're going to see something that people will talk about for years. I mean, think about it. No more bulky warp engine or nacelles. A ship just generates a soliton wave and then rides it through space like a surfboard.
Now, of course, that's not what I had originally learned about solitons. However, as I said, the word somehow infiltrated not just science and engineering and math, but popular culture. And just recently, my wife was at an event I couldn't go to, and she met some people, and they said, well, what does your husband do? She says, well, he's a mathematician. And they said, well, what kind of math does he do? She said, well, he does waves and such. And they, oh, what kind of waves? My God, I got that narrow. He said, well, these waves called solitons. They said, I know about solitons. That was on Star Trek. So how many times you work in a field where the essence of the field is somehow morphed over the time you've been in it, because I've been in it a long time, and you have this popular culture, and you can follow it more on from the literature on Google, and just type in solitons and find a whole lot. Any rate, let's talk more science here. Where else can you see solitary or localized waves? Well, one area is the great red spot of Jupiter. This is a stable, localized wave, been observed for over 300 years. Spot's very large, and the dynamics still under investigation. This is not an integrable system, but it's a very interesting one, and there's your spot. It's just staying there, obvious that it exists, localized. Another type, morning glory. These are roll clouds, and they're, in the language of today, line solitary waves or line solitons. And they come in areas of Australia regularly and other areas of the world. And here's a side view of a roll cloud. You can see there are others behind it. And this is another view from an airplane. And you see, here they are. There's a sequence of them. And there's another program that's going to go on this summer, starting this summer here at the Newton Institute, called dispersive shock waves. And if you look at them, they have remnants of solitons in them. The front part are soliton-type waves. And if you just like nonlinear waves, but we don't know much about how to solve these equations, when they break, pull out your surfboard and go to San Diego, and you'll enjoy it. Okay, let's look back where solitons mathematically came from. Okay? Well, they were first discovered in water waves, in viscid water waves, and in fact, the fundamental equations of fluids by Euler was set out by him, and he was blind for many years. And there you can see a droopy right eye, and he was, of course, a profound mathematician. And then a few years later, Laplace studied water waves, small amplitude, shallow water waves. And we know about Laplace's equation, and in fact, it plays a role in ideal fluids and in water waves. And some of what I have to say in the next couple of slides comes from the Annual Review of Fluid Mechanics by Craik. did a study of the history of order waves. Very interesting. I have only a few things to say about that. 1813, the French Academy of Sciences announced a prize competition in water waves. And Cauchy was awarded the prize. Poisson was a judge on the committee. He also strangely submitted a paper because he was very interested in this subject at that time. He published it in 1818. Cauchy won the prize, but took him a few years, 1827, to eventually publish his work. The pressure for publication wasn't as great, I guess. It was a complicated method, had to do with Fourier, the beginnings of Fourier analysis as we understand it. Now, Cauchy, why I brought him in, is he was a pioneer in complex analysis. It's astonishing the contributions he made in complex analysis that we use today. Truly amazing. And there is Cauchy and Poisson, early portraits of them. Now, moving ahead to the 1830s, the British Association for the Advancement of Science set up a committee on waves, 2 members. One of them was John Scott Russell, an early portrait of him. And he wrote three papers. The big one was 1844, and I'll quote some of what he had to say. He had to say so much I couldn't possibly quote this. But he's such a beautiful writer. I was observing the motion of a boat drawn along a narrow channel by a pair of horses. The boat suddenly stopped, not so the mass of water in the channel. It accumulated around the prow of the vessel in a state of violent agitation. Suddenly it rode forward with great velocity, assuming the form of a large, solitary elevation, rounded, smooth, well-defined heap of water which continued its course along the channel, apparently without change of form. I followed on horseback in Suchum the month of 1834. It was my first chance interview with that singular and beautiful phenomenon, and it is indeed true. He spent a lot of time studying this phenomena. He called it the great wave of translation. I don't know who termed it solitary wave, but certainly he had it there. He did experiments, and he demonstrated solitary waves, and he found a speed-amplitude relationship, and I'll bring that back later. He called it the great wave of translation, later the solitary wave. Here is some plot of his experiments. He had a channel, a little canal, and it's easy to create a solitary wave, which he did, and you're looking at the side of the channel, and it propagates with a speed-amplitude relation. And I note he even looked at interacting solitary waves. But this was a case where the small one was behind the big one. Had he looked at the big one behind the small one, maybe history would have changed, as I'll talk about later. He also had depressive waves and solitary waves. I'll talk about depressive waves a little bit later. Here's a video, in case you didn't have a good feeling for this. Here's a video of a solitary wave in a little canal, a little channel. There she goes. Easy to develop, easy to move. Whoops. Sorry. He was also prominent in shipbuilding, and he used the concept wave of translation to design ships. And Physics Today, July 19, 2017, has a long article about shipbuilding and his role and how things have changed. And this is the launch of the Great Eastern. There you have the Great Eastern. This was a sail and powerboat at the same time. And he used a lot of the ideas of building these boats from the Great Wave of Translation. And there he is, a later picture of him. And there is his colleague, Isam Brunel, who's a well-known British engineer. But unfortunately, this Great Eastern wasn't so so successful, because they had backup sales to the powerboat, because early on, I guess, powerboats weren't so reliable. But later on, people gave up on sails when they wanted to transport people and machines. And Russell said, it now remained for the mathematician to predict the discovery after it happened. Well, we do a lot of that. I'm okay with that. But then leading fluid dynamics researchers doubted the importance of the solitary wave and thought it was linear, and notably Airy. Now, Airy was working on, you might say, Inviscid-Berger's equation. They thought all nonlinear waves had to break. So how could this not break? Because he didn't understand the higher order effects were critical. And there's Stokes, 1847. He found a nonlinear periodic wave. And he found the speed depends on the amplitude. Major result. He did not, in those days, early on, apparently believe, Scott Russell, despite the fact that speed-amplitude relationship was critical, and that's not something you see in linear waves. So it took him quite a while to come around. He made many other critical contributions to fluids. Can't ignore the fact that he came up with the Navier-Stokes equations, which we use every day. And this is sort of the difference between applied methods and pure methods. Well, we're not going to stop because we don't have a proof that the solution doesn't exist. But it's critical to prove it. And if you're bored with this lecture, I encourage you to try to prove this and collect $1 million. He doesn't look so happy, but he should have been. Well, 1870s, Boussinesq, here he is on the left, and 1890s, 95, Korteweg and his student de Vries studied shallow water waves. Boussinesq was mainly interested in waves in two directions. Korteweg and de Vries, unidirectional waves. They both found solitary wave solutions to their equations. Korteweg and de Vries found a conoidal wave, nonlinear wave, which is a special limit, is a Sèche profile, or if you will, solitary wave. So at the end of the day, Russell's work was confirmed. Here in 1995, you have this aqueduct, and you have a boat sitting out there, and you sent the boat down that little aqueduct. 12 years earlier, researchers tried to do it, not on this aqueduct, but further in on the Union Canal, to reproduce what Scott Russell saw. And they, the first time was not successful, but the second time was. This boat goes down the channel and stops and sets forth a heap of water, which is a solitary wave. So everybody felt good. And you see that guy over there? Can you see that, Peter? That's an early version of Peter and Martin Kruskal. Between 1895 and 1960, Korteweg de Vries mainly a water wave operation. But in the early 60s, mathematicians and physicists developed methods to derive equations in a clear way. And they were able to derive the Korteweg de Vries, and later I'll talk about nonlinear Schrödinger equation, as two important universal equations. Universal is a statement that certain phenomena occur in these equations that you can understand how to get from governing physical phenomena like water waves or other circumstances, how you get down to the basic equations and why you expect KdV to occur in many different physical circumstances. And in fact, Kruskal in the 60s was interested in the Fermi postulum problem, which was springs masses, and he gave a lecture at Princeton. And the lecture was on open problems in applied math, and one of them was the Fermi postulum problem, which said, I have spring masses, and I start with energy in a single mode. The energy they expected to go to all the higher modes, but they didn't. When energy went up, and then it coalesced back, and went up and went back. Sort of recurrence of initial states, which they found, Fermi and Pastor and Ulam found using very crude numerical methods. And in fact, KdV was derived for that system, for the Fermi-Pastor-Ulam spring system, by Kruskal. And he gave this lecture, and he said, well, can we explain the Fermi-Pastor-Ulam problem in a clear way, why there was this recurrence of initial states? And in fact, they did. And the reason they did is they came up with the concept of solitons as the reason why energy had to occur. I'm not going to go through that piece of it, but I'll go through the calculation in a bit to explain what a soliton was and is. So, 65, by the way, that paper by Kruskal and Zabusky is considered a 50-year milestone paper by Physical Review Letters. In 67, Pearel again, a method to find the solution of the quadratic de Vries equation by Gardner, Green, Kruskal, and Mura. And they associated solitons with eigenvalues of an important linear equation, the time-independent Schrodinger equation. This was enough to get people interested. And I was a student at the time, and I remember my advisor, Dave Benny, saying, look at this, which I did. This was incredible. And if you ask me, if you say, well, I found some more solutions to an equation, okay, might be interesting. But to have the profound impact it had to be something really deep. And the depth was that solitons, these special equations, special solutions of special equations, have to do with spectral theory, eigenvalues of important linear equations. And there's more to be said about that. In the 70s till today, these developments led to new methods and results in math and physics. And researchers across the globe had major impact. The United States, Russia, Japan, UK, etc. Many very important discoveries. Now, there's so much, I'm not going to go through all of it. It's impossible. But I did give, in my earlier lecture at Newton, some indication of who fit into what in those days. But I will say we came up with this idea of how to look at these problems. We called it the inverse scattering transform. My colleagues, Dave Kaup, Alan Newell, Harvey Seeger, and myself, where we found a broad system of equations. And solitons were eigenvalues of this associated linear equation, which, of course, just extended what was done earlier in Gardner, Green, Kruskal, and Mura in that famous paper, and also Zakharov and Shabbat in a very important following paper in the early 70s. And KdV is an example of an equation solved by this inverse transform method. And we call it integrable equation. And there are a whole pile of wave equations that you can solve by this method. Partial differential equations, discrete equations, integral differential equations, important ODEs, and the like. And even today, even the last few years, we've found many new nonlinear equations. And I talked about that in my prior lecture at Newton. Now, what is IST all about? In words, you associate the nonlinear wave equation with linear equations. If you don't have a way to linearize it, it's not going to work. The direct problem, you take initial condition and you transform it to what we call scattering data. And there's special numbers called eigenvalues. That's where the solitons come from. We take that data, go to the scattering data, we evolve the scattering data in time, thinking of this as space-time. And then we do inverse scattering, inverse, to find the nonlinear solution. It's analogous to linear problems, linear Fourier transforms, except the mathematical study is one of linear integral equations, not integrals. Fourier transforms are hard enough, but now you have linear integral equations, so at various times things get a little hard. And here's KdV's equation from their paper. Eta is the wave elevation. Could be positive or negative. eta sub t means partial of a with respect to t, and eta sub x partial a with respect to x, etc. And the dimensions, you have gravity, mean height, and this thing, normalized surface tension. If the surface tension is small, like it usually is in most applications, this is a positive number, and you have a wave of elevation as the solitary wave. If this is negative, you have a wave of depression, and both have been observed in the laboratory. It's harder to work with large surface tension because the fluids are difficult to work with, and typically it had to work with mercury, and that's really tough. But this was observed. Now, mathematicians like to non-dimensionalize equations, so this is the equation after you remove the dimensions. And here's the solution, a solution to this equation. Hyperbolic secant squared, that's typical hyperbolic function. And the amplitude's 2 kappa squared. The speed is 4 kappa squared. 2 to 1, that's exactly, when you unwind the dimensions, what Scott Russell observed. So Scott Russell was spot on. And kappa is the eigenvalue, which I'll only say is a special number. I'm not going to go through the details here. And there's a picture of a solitary wave. And here's a video of it. Moving along. And if you recall that solitary wave in that canal, it's exactly the same concept. So what did Kruskal and Zabusky really do? They found more than one solitary wave. They found 2. And that's the difference between solitary waves and solitons. What happens when you have more than one? Well, not only can you solve the equation, that's one thing, but look what happens. The big one's behind the small one. If you recall, Scott Russell had the small one behind the big one. The big one moves faster than the small one, and they interact. And the big one comes out with the same amplitude and speed as the small one with a phase shift. That's the only thing that's a remnant of the nonlinearity. Phase shift. And you can do this with 2 or 3 or any number. I only have a video of 2. Whoops. Here's what happens video-wise. I like videos because it really gives you an understanding of what's happening in a nice way. There you go. The big one goes right through the little one. And so, okay, I showed you a solution. I could have shown you 3, could have shown you 4. But in fact, KdV is special, not just because it's related to eigenvalues. That's only part of the story. There's another part. What we studied back in the early days is the dispersive tail. You take a hump, and it goes, there's some solitons that go out. At time 0, you can find all the eigenvalues. You ask somebody to compute a certain eigenvalue problem, get all the eigenvalues, and people did that in experiments. But they leave behind a dispersive tail. And we studied that heavily. And this dispersive tail is related to equations studied by Painlevé. There he is. There's his dates of his life. And what we found, not just for KdV we found that the long-time asymptotics had a portion of it that was dominated by the solution of an equation found by Painlevé. But then we realized this had far broader consequences. And every equation we touched that was integrable, we take similarity solutions or reductions and find Painlevé equations. And we gave a description of this by integral equations of what happened to it. And we found that they had similar properties, and these properties are all complex variables. This is all complex analysis. Namely, in the complex plane, equations in the complex plane only have poles. And this is what we found. The study of Painlevé equations was less fashionable in the 20s through the 70s. And in the 70s, people found it in other applications. But in inverse scattering transforms and soliton theory, you found it as a prevalent feature. And if you ask me, And I'm telling you my opinion here. That's one of the big reasons why Pain-Levé equations became a whole lot more popular. It wasn't one system. It was one application. It was mathematically very broad. And I point out Pain-Levé and his students and colleagues found 6 Pain-Levé equations, and we can consider them as new special functions. And today, research still continues on Pain-Levé equations, and I encourage you to read Peter Clarkson's discussion of Pain-Levé equations in the Digital Library of Math Science, Digital Library of Math Functions, and you see that Pain-Levé equations have made it to the popular mathematical literature, to the standard mathematical literature. And again, complex variables is central. There's Paul Pain-Levé, and when you go to Paris, don't leave without going to Square de Paul Pain-Levé. Right there. It's very nice. You remember the French Academy, twice war minister, twice prime minister for short periods. Entered in the Pantheon. I'm turning my attention to the KP equation. This is a 2-dimensional generalization of KdV. Very simple, actually, and was the first, to my knowledge, 2-space one-time equation be solved by inverse transforms and be known to be integrable. We derived it after they derived it in the context of plasma physics. We derived it with Harvey Seeger in shallow water waves. And again, there are 2 signs. Strong surface tension, you find lump solutions. Small surface tension, you find line solitary waves. Let me tell you about those. Here's the KP equation in normalized form. KdV, 1 derivative, plus 2 transverse derivatives. And there are 2 signs. Small surface tension, we gave it the name KP2. Don't know why we chose that, but we did. And here's the equation. And the simplest soliton, line soliton solutions are due to Satsuma, 76. And here's just one of them. Just moving along. It's not really 2-dimensional, it's 1-dimensional. And if you want to know what it means physically, go to Hawaii. This is where this picture was. And there's a line solitary wave right there. And if you look closely at the smaller amplitude stuff, it looks just like a SESH profile. But I'm talking more today about interacting solitary waves, interacting line solitons. And you see that? We call that a small x. And there's a parameter in these solutions, e to the a12. And there are 4 cases. E to the a12 order 1, large, small, 0. So this is order 1, and this is large. So the stem expands. The guy in the middle is bigger than the sides. And this is e to the a12 small. And when e to the a12 goes to 0, these things spread out, leaving just one of them. This solution was found by Miles, 1977. Now, if I'm going to tell you something that doesn't seem to be physically reasonable, these guys come up every day on beaches throughout the world. And here's a picture I took in Nuevo Vallarta, Mexico, where we go every winter. I get there for a month and a half, squeeze out. I'm like an undergraduate. As soon as classes are over, I leave. Classes begin, I'm there the day before. So here's 2 interacting solitary waves, line solitons, and there's that little peak. I show you the picture, and I show you this little hump here. Okay, that's the analytic solution. Okay, it's not perfect. Well, remember, water waves, you don't clean water waves. This is not like you do a laboratory experiment where the water is clean and you let it sit for a day or 2 days, whatever. This is the ocean with all the dirt and rot and whatnot. Okay? E to the a12 order 1. Here's a guy walking on the beach in Nuevo, and there's a little X wave. He doesn't care about that, but I'm just showing you how shallow the water is. And then a second beach. I encouraged my student at the time, Douglas Baldwin, to go to another beach. He said, well, I'll go visit California. So he drove out there with his family. And here's a second shallow, flat beach. 2 to 5 inches is what you need. Within 2 hours of low tide, we observe X and Y most often. Being near a jetty is useful because the waves can come in and interact with the dominant wave coming in. Otherwise, wait till the afternoon. After I took these pictures, we published a paper. We got a deluge of photographs from other areas in the world. Here's e to the A12 large, a long stem. This is California, this is Mexico. And that's the top view. Here's an H wave, which I have to grant Douglas figured that out. He says we're missing one limit. So we went out and found it. The H wave. Guy is smaller in between. And here's the Y. 2 pictures. Now if you add, oh yeah, and there's others. KP has a menagerie of solutions. Here's 2 coming in, 3 going out. And there's a lot of research in this. Kodama, Biondini, Chakravarty, and Kodama has written a book on the zoology of these waves. It's fantastic. We see the X and Y's most often. And here's an egret just looking at an X wave. And the paper was published in PhysRev. Let me show you a video that I took of 2 cases. We'll do the short stem first. You see, it's in shallow water. That's a more complicated case. Okay, get rid of this. Now let's do Y. Y coming out, there's a bigger one. There's a nice one. Egret getting out of its way. Point is, if you look at them for a while, you understand what's going on, you realize that when they're going to rise, and if you look more carefully, you can see the interaction, just like the theory predicts. Here's another sign, KP, the minus sign, KP1, and here's a wave. You have a hump in this direction, a little divot. Oops. Here, it's a better case. There's KP1, and here is the x equals 0, and here's y equals 0. Notice that indentation. I'm going to come back to that, mention that again next time. And there's a whole class of multi-lump solutions, higher order lump solutions. There's not just a simple solitary wave, as this is, or soliton, but there's higher order solitons. And we studied these extensively, and there's a lot of interest in them. But that has not been observed in the laboratory, by the way, because there's large surface tension, and you have to have a big, wide tank. So I don't know how easy it is to work with large surface tension in that case. Let me summarize the first part. We talked about localized waves, solitons, solitary waves, historical discussion, KdV, integrability, IST, solitons as eigenvalues, Pan-LeVay equations, and then as an application, multidimensional water waves in KP. Let me turn your attention to more applications where solitons play a role. Rogue waves. A rogue wave is considered as one which is substantially larger than its background. So if you have a background of a couple of feet, then a rogue wave would be 3 times as large, say 6 to 8 feet. And people who have been in the ocean talked about currents of huge waves called rogue or freak waves. They just seem to come out of the blue. And some mechanisms for this. And is this folklore? Well, I'll show you why we don't think it's folklore. And people have gotten very interested in this. Early on, people thought of currents and winds as being important. I think more recently, people are looking at nonlinear features. Rogue waves can be walls of water coming into a vessel, or holes, just a hole in the water all of a sudden. It can be very substantial. Look at the damage caused by some of these rogue waves. And I was sent a paper recently. I don't review very much because I get an enormous number of papers to review. But this one I did. It was for an ocean magazine or an ocean paper. And they said 300 documented rogue events in the last half a dozen years. It's amazing. And why do we think this is not trivial? This is not just a figment of our imagination. In 1995, a big wave pressed across 95 feet was observed and measured off a platform in the North Sea called the Dropna wave, the Dropna platform. You see this big wave, and it occurred, and they said, wow, this is amazing. So there's a lot of interest. And we'll go back to Stokes. Remember I said he had that periodic wave, and it was unstable. Well, what is the dominant effect of that instability? It's a partial differential equation, the nonlinear Schrodinger equation. You see this nonlinearity here? That's what we would call a Schrodinger equation if that was a given external potential. No, it's nonlinear feature. And psi is the envelope of the wave field. So you have waves inside an envelope. And this envelope satisfies nonlinear Schrodinger equation. And that's a typical case when you go to 0 at infinity, called Sesh profile. Soliton, eigenvalues, the whole thing. And it occurs in many fields. Water waves, optics, two notable ones. Integrable. And there's another solution when you don't go to 0 at infinity, you go to a constant infinity called the Peregrine soliton. It's a rational function. You can get at it by limits of exponential profiles. And it was measured in optics in 2007 and subsequently water waves 2011. Here's a picture of it. It's not so clear, but in one direction, in the temporal coordinate, it's like a hump, and in the spatial coordinate, it's got a little indentation, just like KP. And this was measured profile in optics, 2007. Pretty decent. That's the crazy thing. Once you are onto the right theory, it doesn't matter. You even if they're higher order terms, what have you, you get the dominant profile. Here's water wave envelope and the water wave measured structure, and blue is the measured profile, and red is the theory. So it's pretty good. The envelope is, you have to put an envelope on these waves. And there's higher order solitons, the relatives of Peregrine. Oh yes, Peregrine, should have pointed out, has an amplitude of 3. So its background is 1, the amplitude is 3. So it just fits this profile. And you do numerical experiments, and these things come out. They're very much like attractors, if you will. They want to come out. And there are higher order relatives of Peregrine. Can have an amplitude 5 times the background. And they're interacting rogue waves. I studied with a colleague, Theodore Sirikis. They can also give 5 times the background. There are lots of ways you can get big events. Let me give you, from this paper of Chabchub et al., 2012, a little movie on I guess this will be good enough. It's moving along. That's a little Lego ship, just getting there, feeling good about itself. And then I'll move this ahead just a little bit. There comes the rogue event. You see it? Right up there. And there you're in the ship, happy, not knowing, and then all of a sudden you see in the up ahead a big rogue event, a super rogue event. Ow! So I guess the point is this can happen. Let me turn your attention to photonics, and we'll talk about photonics and cellular automata as examples. Solitary waves and waveguides, they take an optical material, they carve in higher index of refraction waveguides. They put in a laser beam here. They measure the field at the other end. And the input beam, if it's weak, the wave disperses or diffracts. When it's stronger input power, the wave develops focusing structure, and then you get a stripe just down the first couple of waveguides. They call this a discrete soliton. This was done in the late 90s by Silberberg's group in Weizmann Institute. Then they looked at square lattice. Blue is high index of refraction, red is low. The governing equation is nonlinear Schrödinger with an external potential being the index of refraction that tells you about this high-low stuff. And they found what they called lattice solitons. Weak input power, let me go back here, you have optical material along a structure with different indices of refraction according to this structure here, and input weak, output strong, input weak, it diffracts, input strong, it coagulates to what they call discrete or lattice soliton, lattice solitary wave. These are not integral to our knowledge. And then people studied honeycomb lattices, where you make a different lattice, a honeycomb lattice, as I'm indicating here. And these are hexagonal creatures, not rectangular, and each spot, each dot, in a simple lattice, you can get at by V1 and V2, the lattice vectors that span the two-dimensional structure. Here you have to start either on the blacks to get all the blacks through the V1 and V2, or all on the whites. Now, honeycomb lattices are very popular. They arise in graphene, ultra-thin carbon material you've probably heard about, and first demonstrated in 2004, Nobel Prize a few years later. Here we're talking about photonic analogs, where you have a photonic structure with these high and low index of refraction. And here is a physical picture of the index of refraction, high in the blues and reds, low index of refraction. I like this because it has a nice Star of David structure. And the dispersion relation, if you go to these equations, there's dual space. There's physical space, where you saw the honeycomb structure, and then there's the, if you will, Fourier or Briand zone, as they call it, where these structures touch at certain points. Honeycomb structure in the dual space. So what am I going to talk about? Well, Haldane and Ragu in 2008 said they're interested in Maxwell's equations with honeycomb background. And they were able to find certain kind of material, or they proposed certain kind of material, which had the effect of changing the index of refraction, if you will, or the material properties. And they broke that, broke this touching of points, these conical singularities. They broke it. And they were able to show that there was underlying topology indicated by Chern numbers. And they found edge wave states. Now, this is all theoretical, but within a year, people at Joannopoulos' group found this experimentally in magnetic systems. And they found edge waves. And the importance of these edge waves is they move along, they're only unidirectional. They can't have backscatter. So if you put in a defect, it just goes right through the defect. So needless to say, there's a lot of interest in this. I point out that George Stokes, our friend, found edge waves in water. Those edge waves are presumably not topological. These are topological. And a few years later, Rexman and Segev's group found photonic material that had this property. And it's a very simple experiment. If you take these rods, high-index rods, you build them into your optical material, and they all go uniformly. Then they take a second experiment, and they take the optical material and put it in a helical structure that breaks time evolution, breaks the symmetry, and they observed these edge waves. And we began studying this shortly thereafter, and we developed a simple mathematical model, not so simple, but a mathematical model called type binding, and we found these edge waves. And we put in nonlinearity, and guess what? The envelope satisfies nonlinear Schrodinger equation. These are solitons. Okay? And so I'm going to show you a movie of solitons you put in here, propagate around, come back, and go all the way around. These are edge waves. There's a parameter in the system. The parameter is such that, yes, that's not working, but the parameter is such that in some regime it's topological, namely there's non-trivial Chern numbers and so on, and other regimes it's not. Whoops, back. There you go. How well you can see it, but there they are. There's the edge wave, just on the edge. You illuminate an edge, and then it just goes right around that material. Much more exponentially localized on the left and right sides. And if you change the parameter, then the edge wave goes down and reflects. So you have a little knob that you can turn the topology on or off, if you will, in the Brion zone, breaks these Dirac cones. And it goes down, goes back up, goes to the top, reflects, and comes back down. Okay. Let me talk about cellular automata the last couple of minutes. I'm going to talk about the game of life. Many of you have probably heard about this. It's 2 dimensions. You take a little neighborhood, 3 by 3, and you take this checkerboard, you go from checkerboard to checkerboard to checkerboard. Time is 0, 1, 2. And there's a rule due to Conway. And you get, if you start here with a 0 or 1, you'll get a 1 if at the center point there's exactly 3 ones. Ones are alive, zeros are dead. Or 1 if there are 2 or 3 living cells. Otherwise you get a 0. Death due to loneliness, perhaps. And there's a ton of localized solitary waves in this game of life. Is a block, just stays there. The beehive just stays there, doesn't move. There's a blinker that is oscillating. And then there's a whole bunch of others, and I was giving a lecture years ago, and somebody said, did you hear about the spaceship? You remember Star Wars? Well, there's a lot of people studying game of life, and they came up with a spaceship. And my daughter, who was looking for a project, she was a little bit younger those days, she said, well, Stephanie, she's a good math student now. She's a cardiologist, so she doesn't do any math. At any rate, she helped me with the spaceship. She found the spaceship, and she programmed it. And here you go. Let's see if I can open this up. Yeah, sometimes it works. There's a spaceship in the game of life. Great. So what did we do next? I said, well, Stephanie, let's interact them. Are they solitons? What do you think? We'll see. Go to the lending betting parlors. They're going towards. Guess they're not solitons. Okay. Last remark about cellular automata. We're done. They're 1D cellular automata. You take a line of zeros and ones, you propagate them to the next step and the next step. And there's one particular model that has solitary wave solutions, a plethora of them, just like the game of life. They were introduced by Park, Stieglitz, and Thurston. That's Bill Thurston, yes, Princeton. And they called it the parity rule filter automata. And there are different types, and the type that they didn't look at were the explicit types. You take xi with r neighbors to the left and r neighbors to the right, and then just depending on those, you get a new update, a new value. Those were studied by Wolfram. He's the developer of Mathematica, but he didn't study filter automatas. Filter automatas are quasi-implicit. To get this value, you look at all the neighbors at the top at t, and then the neighbors to the left at t plus 1. It's quasi-implicit because you put everything on compact support, and you go from, take the stencil, move over, until you hit a non-zero value. And the non-zero value will give you a change from what you had from zeros. And I'm a believer in simplicity, and the rule they came up with is really simple. They just sum all the guys at the top and all the guys at the bottom, and they get the new values 1 if the sum is even and non-zero. Otherwise, 0. Just one little change from even odd. And you take a general initial condition of zeros and ones. We're talking cellular automata, just zeros and ones. Let it propagate, and you get all these particle solutions, solitary waves. You interact them. Beautiful. They interact. You go to the sum. You plot the sum. My God, you say these are solitons. They got to be. But then we studied more carefully. And there's reversibility. We cleaned up the reversibility with Jim Kaiser and Leon Takhtajan, and played with it, and eventually had to change a lot. Got Jim Kaiser a job at the National Security Agency, and found an application, encryption and decryption. And here's secret codes. Here's it encrypted, because we now have a reversible rule with lots of knobs and bells and whistles. Here's Dracula with those knobs, 1 knob, 2 knobs, 3 knobs, till you get nothing. Okay, let me summarize, and we're done. Soliton's keen scientific and popular interest. Talked about John Scott Russell, great wave, solitary waves. And then the concept of solitons, inverse transform, and eigenvalues integrability. They arise in many areas of physics. I just talked about a few today. Beaches, rogue waves, photonics. Waves that's also zeros and ones, the simplest waves around, game of life, and the parity rule filter automata. 5 o'clock. Thank you. Yeah. We did. Right. So there's, you start with the nonlinear Schrodinger equation with a lattice. Okay. Then you put in Kerr nonlinearity. See, it's chi3 nonlinearity. And then when you do the tight binding approximation, the only thing that occurs, tight binding looks at nearest neighbors, but with nonlinearity, nearest neighbors are self-neighbors. And that's how you get the dominant interaction. So it's a NLS discrete system, but then when you put in an envelope, you can create a NLS, continuous NLS equation. And the continuous limit, because you put in an envelope over many neighbors. Chi3, and otherwise you don't have nonlinearity. And so we're one of the few groups that add in nonlinearity. But it's just a matter of time until they get to it. Yeah, it's feasible, and there's interest, but right now the physicists are very heavily interested in the linear systems and different kinds of linear systems that give you these edge waves. And they are exponentially localized. In all the cases I know, although I point out that the exponential localization from zigzag boundaries for honeycomb is much stronger than from armchair top and bottom. It's a weaker exponential decay.
When you net three solitons of amplitude A under a certain angle line, then the KP equation shows you series maximum case, which you can get 8.6 A. That was actually inspired by the artwork of steel structures which you find just around the corner. Where you see a realization outside, that remains to be seen, but I informally said that they could get to that situation in 6 years.
Right, and I point out to you that that article I reviewed talked about rogue waves both in deep and shallow water. So KP is a shallow water thing, but you know, in a harbor, you could have waves that are very long, and they could create a big event. So I would classify that as a super rogue KP event.
I believe that the reception outside, so I invite you to thank the speaker again for the reception. Very clear.
Thank you.